heat transfer. It's this invisible dance of energy that shapes literally everything, from our morning coffee to the climate of our entire planet. In this explainer, we're going to go way beyond the basics to really understand the deep physics that govern this whole process.
Now, just a quick heads up, this is an advanced explainer. We're going to assume you've got the basics down. Maybe you saw our last video on this. Today, we're building a much more rigorous framework for looking at thermodynamics.
So here's our game plan. We'll kick things off with the first principles of heat energy. Then we'll break down the three big modes of transfer: direct contact, fluid motion, and radiation. After that, we'll pull it all together to analyze a real system, and we'll wrap up with 5 core principles you can take with you.
All right, so first things first. Before we can even talk about how heat moves, we need to be crystal clear on what heat fundamentally is. Let's get our first principle straight.
At its absolute core, heat transfer is just thermal energy on the move. And the one thing that makes it move? A temperature gradient. That's the key. If there's no difference in temperature, there's no net movement of heat. It's just the universe trying to find its balance, seeking that thermal equilibrium. So that brings us to the big analytical challenge, right? When you look at any real-world situation, you've got energy moving all over the place. How do we scientifically untangle all that and figure out what's actually happening? Well, we can use this simple 3-step diagnostic. It's actually a really powerful way to deconstruct any thermal system. So you ask yourself, step 1, are the objects touching? If they are, you're looking at conduction. If not, you go to step 2. Is there a fluid, like air or water, in between? If yes, that's convection. And if the answer to both is no, well, then it has to be radiation. Let's dig into each one. First up, we've got conduction. This is the most personal form of heat transfer. It's happening right at the molecular level. Now, the key thing to get here is that the material itself isn't going anywhere. It's just the energy passing through it. It's kind of like a chain reaction of vibrations. The more energetic molecules are basically just bumping into their neighbors and passing that energy right down the line. And of course, how fast this happens depends on what the material is, how thick it is, and the temperature difference that's driving the whole thing. Just picture this spoon sitting in a hot cup of tea. The super fast-moving molecules in the tea are slamming into the tip of the spoon, transferring their kinetic energy. Then that energy gets passed up the solid metal, molecule by molecule by molecule, until the handle you're holding gets hot. That right there is pure conduction. Okay, so we've moved on from stationary solids. Now we're diving into the dynamic world of fluids. What happens when the medium itself can actually move? This is where convection comes in. Here, the medium itself is the messenger. So as a fluid like air or water gets heated, it expands, it becomes less dense, and it starts to rise. Then cooler, denser fluid moves in to take its place, gets heated up, and it rises too. This whole process creates a continuous circular flow that we call a convection current. A boiling kettle is the absolute perfect example. So the heating element at the bottom heats the water it's touching through conduction, right? Then that hot water expands, gets less dense, and rises, physically carrying its thermal energy with it. Cooler water from the top sinks to take its place, and this whole circulation gets going, heating the entire pot super efficiently. And believe it or not, this exact same process, just on a massive scale, is what drives ocean currents and our planet's weather. So let's just pause for a second and compare. The critical difference here is the movement of matter. In conduction, energy gets passed through a fixed medium. But in convection, the heated medium itself moves, carrying the energy along for the ride. That is a really fundamental distinction. And now for our third, and maybe the most mind-bending, mode of transfer. What in the world happens when there's no contact and no medium at all? This is radiation. It has nothing to do with molecules bumping or flowing. This is energy being shot out as electromagnetic waves, mostly in the infrared spectrum. And what's wild is that any object with a temperature above absolute zero, from a massive star to your own body, is constantly radiating this energy. And the amount of energy it radiates goes up exponentially with temperature. So a red-hot piece of metal isn't just a little warmer. It is radiating a ton more energy. And honestly, this is the most profound example there is. There's this vast, empty vacuum of space between us and the sun. Conduction is impossible. Convection is impossible. The only way the sun's incredible energy can reach us and make life possible is by traveling as electromagnetic waves right through that void. And
Here's another thing that sets it apart, really highlighting its wave-like nature. Just like visible light, thermal radiation can be reflected by a mirror or bent by a lens. This property is exactly why those shiny reflective emergency blankets work so well. They're literally reflecting your body's thermal radiation right back at you, keeping you warm. Okay, so we've looked at the three modes separately. Now, let's put it all together and apply our framework to a real-world scenario where all three are happening at the same time. Take a close look at this campfire scene. We've got a fire, a pot, and water inside. This is a perfect little thermal system. So using what we've just talked about, take a second, see if you can pinpoint where conduction, convection, and radiation are all at play. All right, did you spot them? Here's the breakdown. Number 1, electromagnetic waves, that's radiation, travel from the flames to the pot, heating its surface. 2, that heat then travels through the solid metal of the handle, that's conduction. And 3, inside the pot, convection currents are swirling that water around, distributing the heat throughout the liquid. Boom, all three at once.
This table really sums up those key differences for analysis. You can see the mechanism shifts from direct contact to fluid motion to electromagnetic waves. The need for a medium just completely vanishes when you get to radiation. And check out the speed. Radiation moves at the speed of light, making it way, way faster than the other two. These are the core distinctions we're always looking for.
We've covered a ton of ground, so let's boil everything we've learned down into 5 essential takeaways. All right, let's lock these in. 1, heat is just energy on the move, and it's always driven by a temperature difference. 2, conduction absolutely requires direct physical contact. 3, convection depends on the bulk movement of a fluid. 4, radiation is energy transfer through electromagnetic waves, and it needs no medium whatsoever. And number 5, which is so crucial for real-world analysis, in most systems you look at, all three modes are happening at the same time. The real challenge is figuring out which one is the most dominant. Which brings us to a final, really big picture question. Our planet is constantly losing heat out into the cold, empty vacuum of space. Now, considering that 2 of our 3 modes absolutely require a medium, which one do you think is solely responsible for cooling our entire world? It's a great question to chew on. Thanks for joining me for this explainer.